All right, feels like the home stretch of the semester here. Um, only one lab left, lab 10 this week. Sequences, batching, and sim optimization. Sequences and batching are two things that will potentially help you simulate more advanced handling in a simpler way inside Arena. So that allows you to model more advanced phenomena without having to build a whole lot more into it. So it's some nice shortcuts that Arena provides there. And then SimOpt. An opportunity to practice some of automated design exploration inside Arena, which can also be helpful thinking about your final project. So this is sort of a double lab because it covers these things. So it's a 30-point lab, but it's got that 20 points bonus possible. So if so there's plenty of the lab you don't have to do. So but because we're basically it's like two sort of labs in one, maybe two and a quarter or something like that. And that's the reason why I've sort of loaded this extra here. So if you are, we have the drop policy on the labs, but then, if you're still looking for a little bit extra, and of course, extra credit from one category does bleed into your grade weighted by that category's weight. So if you get extra credit in your whole lab grade, then that does bleed over into your total grade. And so there's an opportunity here to sort of make up for some points that you may feel like you've lost earlier in the semester. Part one sequences, part two batching. Also introduces these guys here. Then after that, no more labs. So that time is meant to help you have time to work on your final project and have access to instructional help for looking for support for that. Your final project, we all know about this. The next thing you have to worry about is the final week of classes, the week just before finals week. The Wednesday of that is when your presentation video, 10 minutes or less, and your final report, 4 pages, but you can have an appendix that has a very specific structure, are due, and that will give you also time to do your peer reviews. And so that's what we have to plan for there. Otherwise, the last normal ICA is ICA L. So that's in about 2 weeks then. And then there's ICA M, that is our final exam review ICA. And so that will be similar to the review ICA that went before the midterm. So it is a little longer. It samples from all of the post-midterm ICAs, plus a few more in that pool. Can be taken multiple times. Your highest grade is recorded. So it gives you that opportunity to practice. If you want to practice for questions from before the midterm, then you still have that this ICA-MA practice, which is basically a pre-midterm ICA. And then this ICA-MB practice will be this after this one disappears. Then if you still want it to be available just to have some practice questions going into the midterm, then that will be available. Sample final exams, just like in the midterm, are available on Canvas. But in order to do that, in order to get access to that final exam module, you need to do that lockdown browser compliance test, just like you did before the midterm. And this final homework, J2, is out there. So that is kind of an arena-based homework, synthesizing some things from class and lab. We capture some ABET metrics from that. So we're not going to distribute a solution set. And that is the one homework that will not be automatically dropped. You may be able to use your experience with the process analyzer or OptQuest that you learn about from Lab 10 to make some of these processes a little bit simpler in J2. But J2 is sort of just mild enough that doing it all by hand is not too bad. But I hope it'll get to the point where after learning about the process analyzer and OptQuest, and then perhaps doing J2 by hand, you'll see the value of these tools if you had to do a much larger optimization. So that's all the admin stuff. Hasn't really changed much. Any questions? Hopefully you've got sort of a structure in mind for the flow chart of your final project target and are starting to move at least a little bit toward that. I know there's going to probably be a flurry of activity there before it's due, but at least try to be doing some work in your head so that you just have to kind of put it down on canvas and start going. Okay, so we are now in this this unit is all about estimating absolute performance. The next unit is about relative performance. So what I mean by that is right now we are focusing on methods where you run a sim and you use it to estimate a particular performance metric. The next unit will be if you run two sims, an A sim and a B sim, trying to figure out the best ways to compare which one's better. Is my A policy better than my B policy? In which case, you may not care about their absolute performance, but you do want to know how they sort, how they rank. So here we are caring about building estimators for absolute performance. And so it's always tempting to use point estimates for absolute performance because that's the easiest thing you get out of there. But point estimates are bad in that every time you run your sim, you get a different point estimate. They might be in the neighborhood of the thing that you're actually trying to estimate, but the neighborhood really matters. So if you run your sim once and you get a value of 1 minute, per customer waiting time or something like that, and then you run it another time and you get 10 minutes, that's very different than a sim where every time you run it, it's, around 5.5, 5.5, 6. So that variation kind of matters. And that's the reason why whenever you run your sim, it's important to not generate a point estimate, but to generate these interval estimates. So the idea here is that if your data are IID, so that's independent and identically distributed, which your simulations should be, because we start each simulation replication with a different random number seed, and that should make every replication independent from each other. And because they're running from the same sim, they should be identically distributed. And then if your number of replications is greater than 5, then at a minimum, you should be able to generate what's an interval estimate using the standard error of the mean. This is less meaningful, as we'll see in a second, but it at least gives you some idea of how variable that mean will be, and that estimate will be every time you run that sim. So this basically says that this particular sim gave me an estimate of X bar, but I know that in the distribution of estimates that I would expect to get out of my sim based on the variation that I got in with these data, with these 5 replications, then I would expect that if I were to do another 5 replications and generate, and then I would get values that this would sort of describe the roughly the distribution plus or minus 1 SD, where the SD here isn't the standard deviation of the phenomena you're measuring. The SD here is the standard deviation of the estimates that are being generated. That's why we call it SEM, or standard error of the mean. So then that's basically just the standard deviation of your real data divided by the square root of the number of replications you run. So that is a crude idea of how much variability you'll get. So at a minimum, if you run independent replications of your sim, like in your final project, for example, at a minimum, you shouldn't ever say, we got a performance of, an average wait time of 5 minutes. You should at a minimum say 5 minutes plus or minus, and then give me this, and then indicate that it's a standard error of the mean, so that I know that, okay, there was a lot of variability in your sim or not a lot of variability in your sim. So that tells me how much I could trust that estimate. Now, hopefully, and in many cases, for simulation performance metrics that are generated, but not always, but for many cases, and particularly when we do these types of sims, we also can be assured that the data we're generating are normally distributed. And so by central limit theorem, for example, your performance metric for every replication might itself be a sum of random variables that were generated in the sim. Well, we know that when you sum up random variables, once you get, above 10 or so, then they look pretty bell-shaped. They look kind of like normal distributions. So a lot of times our simulation data are normally distributed anyway, in which case we can go one better and we can generate a confidence interval. So, and usually a 95% confidence interval, but it doesn't have to be. So in homework J2, we'll tell you to convert, I think, a 95% confidence interval to a 90% confidence interval. So, and there are reasons to do that. And so this is much more useful, as the demo that I'm about to do will show, in that this captures all of the hypothetical performance measures that cannot be rejected by a t-test. So you're going to estimate some performance measure from your sim, and then basically anything to the left of it by this quantity or anything to the right of it by that quantity. If you were to do a one sample t-test, based on the data you gathered, you would not anything inside here would have P greater than 0.05. Anything outside would have P less than 0.05. So this summarizes the results of a bunch of t-tests right there. So what that basically means, as the demo I'm about to do will show, is that 95% of the time, your simulation will capture the true mean in this interval. So ultimately, we don't care about X bar. We care about what the true mean is. What is the true average wait time for customers in our system, for parts going through our manufacturer system, whatever it is? That true mean is not going to be X bar. X bar hopefully is nearby, but what is nearby anyway? That's what these interval estimates tell us, is what is nearby. And this, this term here, this half width of the confidence interval, gives us a much more rigorous way to say nearby. 95% of the time, then that real mean will be in this interval, which is a powerful statement. So sometimes your data are IID, but they're not normally distributed. But when you look at the histogram, you might see that they have they're really asymmetric. They have long tails. There are a bunch of things like that, that there are mathematical transformations that you can apply to your data, like you take the logarithm of your data, and then after you get that transformation, then if you histogram it, then you see, oh, that is normally distributed. So then you can apply all your stats and your confidence intervals on the transformed data. It's a little stranger to interpret because now you're saying that it's a 95% confidence interval on transformed data, which you could then sort of untransform, and you get this nice sort of symmetric confidence interval after you kind of go through the inverse transform, might be this asymmetric confidence interval. But that is another way that you can use all of these tools that have been developed for normally distributed data on data that aren't normally distributed, if you can manage to stretch them and skew them in a way that gets them back to normality. And then finally, if your data are not IID, so if you notice that there is a strong correlation, for example, between one replicate and the next, so you can predict one replicate by knowing the previous, then likely you have pseudo replication. And so that would be like if you wanted to measure the average height of the human race or whatever, like their average height of say women in this room, and you randomly drew women in this room, and there aren't that many, and so then you end up getting a lot of repeat individuals, and so you notice that there's an overrepresentation of certain heights, or if you sorted everybody by height or something like that, and then you ran out of time, and you only got the first the shortest people or something like that. I'm sort of coming up with all these kind of this. There are a bunch of different things that could generate. I mean, the biggest thing is let's say you're trying to measure something that evolves over time, and if you can't, like, if you take my temperature, you can take my temperature now, a second later, a second later, a second later, and that will have a certain pattern, and you'll be able to predict one temperature from the next. If you just take my temperature now every millisecond, you get more data, but you don't actually get more data, right? So it's just at a higher resolution. You might capture more dynamic things that happen with me, but regardless of if it's 10 samples of my temperature or 1,000 samples of my temperature, really the sample is the whole series because it's all about my temperature. So that's what we refer to as pseudo replication. Is that in an Excel spreadsheet, it looks like you have more rows, so it feels like you have more replicates, but they're all strongly correlated together. So you have to consider the whole column of data, because it was taken from one individual, as one sample. So that's what I mean here. And for a simulation, what that means is you might generate 1,000 customers in your sim, but that's not actually 1,000 replications. So that's not actually 1,000 wait times, because the wait time of one customer might be correlated with the wait time of next and next and next. That's why I've got to generate 1,000 customers, reset the sim, use a new random number, which a new random number seed, which Arena will do automatically, and then generate a new 1,000. And then the aggregate of the 1,000 is a single performance measure for that replication, and the aggregate of the next 1,000 is a single performance measure of the next replication. So even though I've generated 2,000 customers, I've only generated two independent data points. So there's only two independent replications. So that's what I mean by pseudo replication. So if you don't have this independent property here, then you have to consider the whole data set as a single individual. And that really is at the core of within replication versus across replication analysis. All right, so any questions about this? Sort of a summary of where we've been. Okay, so yeah, so let's do a quick demo to sort of show you what I mean by this confidence interval stuff. Let's say I did go into Excel and I generate rows here. So across here, it's a little tiny, but you can see on the online version of details. But you sort of trust me that basically in all of these columns here, I've just used this, which in Excel, this rand generates random numbers between 0 and 1. This and then this norm inv is the inverse CDF of a normal distribution. And so, and then where that normal distribution has a mean of 5 and a standard deviation of 0.1. So this, by the way, is how you generate normally distributed data in Excel. Hopefully it looks familiar because that's just the inverse transform method. So you've got your Excel readily generates numbers between 0 and 1, and then Excel provides you the inverse CDF of a number of different distributions. One of them is the normal. So you just pop that into that CDF and out you get normally distributed data. And so that's what I've generated here is a bunch of normally distributed samples across these columns. So I've got a row of, I forget how many, I think 18, a row of 18 numbers, and then another row of 18 numbers. And then over here, I then aggregate those. And so I've have the average of this row, the average of the next row down this column. So each cell in this column are the average of these 18 numbers. And then I generate a 95% confidence interval by generating the standard deviation and then the half width. And so over here, I've got the standard deviation of this row, the standard deviation of the next row, and so on. And then I use that to generate my 95% confidence interval half width in here. So that basically takes that standard deviation and divides it by square root of 18 and then multiplies that by the critical t value, which will be around 2. So so that's how I get from here to there. And so basically this mean plus or minus this half width is my confidence interval. So there is and this half width, by the way, I just said how I could generate manually, but there is a routine in Excel called confidence.t, which is how you generate confidence intervals if you don't want to go through the formula I just said, where you divide by square root of n and multiply by a critical t value. It does that all for you in confidence.t. You provide it your alpha, and then it will provide, and you provide it the standard deviation, and you provide it the count of data, and it just plugs into the formula that I just said. So it will take this standard deviation, divide by square root of that. It'll look in the t table for this divided by 2 because it's a two-tailed, and then it'll generate the right half width. So that's what I did. So every row has got basically a confidence interval that's been generated for it. And then I, over here, I know the true mean of these data, it's 5. So then I just said, did this confidence interval that I generate include the mean? And then so I have a column which just says true and false. Did it right here. So is the mean included in the confidence interval or not? So then I fill that thing. So I'm just stepping through there, confidence interval. And then I just fill that down and then I can plot all my confidence intervals. So I've got plotted here. So I've generated, I forget, it probably says on here and it'll see it. Let's say I generated hundreds of rows of this. So right here, let's say 187, that's what it is. I generated 187 rows because I just dragged down until I got tired. And I generated a bunch of confidence intervals. So each vertical line is a confidence interval from one of these rows. The blue dots are the means. And then the true mean is 5, which is right across the middle of the plot here. And then so you can then go through and see, this confidence interval up here does not include the mean, but most of the rest of them do. So that's what we have here. So I can count how many of them include the mean and how many of them don't. So this blue one includes the mean. These magenta ones are the only ones that don't. So there's 1, 2, 3, 4, 5, 6 out of 187 that's roughly a 5% failure rate. So that this by failure, what I mean is this confidence interval detects a false positive. What I mean by that is if the true mean is 5, these data would reject the true mean. And that would be a failure because the true mean really is 5. But if I happen to be unlucky and my sim generated these data and I generated this confidence interval, in this rare case, 5% of the time, I would reject the actual mean from the population. But most of the time, 95% of the time, my sim, like the means, they're all over the place. But 95% of the time, the confidence interval captures the true mean. That is the meaning of the confidence interval. So we can play with that. So a low false positive rate, a low alpha, is going to generate large CIs that always include the real mean. So people would say, well, why 95% confidence interval? Why don't you give me a 99% confidence interval? Well, 99% confidence interval is not that useful because it's gigantic. It doesn't resolve any ambiguity. Sure, it always captures the true mean, but it captures so much else too. So you don't go for really, really high confidence intervals because they don't give you any resolution. 100% confidence interval is the entire real line. You may as well not run the sim if you want 100% confidence interval. You just say it could be anything. That's the only way I could be 100% confident. So I reduce that and I say I'm only 95% confident, but what I get in that trade-off is I get smaller confidence intervals. So a low false positive rate implies large confidence intervals. As I reduce that false positive rate, I get tinier confidence intervals, and as expected, I get errors. Occasionally, I get confidence intervals that are so far away that they actually miss the real mean. But 95% of the time, I don't. So that's good here. So what I've got up here, so by the way, back here, if you're the difference between here, well, these are just all have an alpha of 0.001, 0.001, and 0.001. So I just generated the same experiment 3 times. But here, I've got a false positive rate of 0.05, 0.05, and 0.05. So I generated 100 confidence intervals, 100 confidence intervals, 100 confidence intervals, basically just 300 confidence intervals that I just wrapped into 3 rows here. And like we can see, roughly 5% of those confidence intervals don't include the true mean, the rest of them do. So as I make it narrower and narrower, I get the failure rate I expected, but I also get a narrower estimate of the performance, which is the good thing that I get out of it. So if I go to here, the false positive rate is 0.6. So that's 60% of the time I'm wrong. But look at what happens to the confidence intervals. They get really tiny. So a point estimate is a 0% confidence interval because at that point, you've collapsed these confidence intervals right on top of their means. So that's why point estimates are useless, because every time you run the sim, you get a different point estimate. So you have no idea how far that point estimate is from the real parameter that you're trying to estimate. So that's why we can't just, crank down the false positive rate or that's why we can't crank up the confidence level. And so if we take the false positive rate and we crank it up so that we get really, really high resolution, I guess it's good because, then our confidence intervals look tiny, but the downside of that is that we have so little confidence that the mean is inside those confidence intervals. So that's the fundamental trade-off, is that if you can't sample more, but you want your confidence intervals to be smaller, you have to give up on confidence. And that's what's going on here. So this has a false positive rate of 0.6, 0.6, and 0.6. And as you can see, there is a lot. So these are 40% confidence intervals, and there's just a lot of failures. So more samples means more power. So here I've got a 0.05, so 95% confidence intervals all the way down through here. So this, I did not change the alpha, the false positive rate, but here I've got 20 samples, here I've got 200 samples, here I've got 2,000 samples. So if you want, it's like this trade-off thing that if you want these confidence intervals to be smaller, but them to be just as accurate, you have to pay a cost for that. So if you're not willing to do the trade-off that I just showed you, then you have to pay the cost. The cost is, one of the ways to pay that cost is to do more sampling. And so that's what we got here. If you only have 20 samples, this is the highest resolution I can give you to guarantee 5% error. If you still want 5% error and no higher, but you want these to be tinier, you just got to sample more, and likewise sample even more. And then the other way that we affect our power is more variance. And so if here I've got a 5% false positive rate, so these are 95% confidence intervals, but here I've made the population, the underlying population I'm sampling from, less variable here and more variable down here. So this is a standard deviation of 1, this is standard deviation of 0.5, this is standard deviation of 2. So here, same number of samples, 30 samples, 30 samples, 30 samples in all of these cases. But what differs across these rows is that these are sort of noisier data and these are less noisy. So if you can manage to sample a system that's just less variable, then you need less samples to get the same width confidence intervals. So if we have the ability to redesign our experiment to somehow account for variance that we already know about, like, okay, we know this output's going to be variable, but if we know that temperature is really affecting the output, and so if we just measure the temperature, then we maybe can subtract off the variance we know that just comes from temperature. And that way, when we run multiple replications that just happen to be at multiple temperatures, then we can subtract off that sort of parasitic variance that we get from temperature because we've controlled for temperature. And that's a way to reduce the variance. And that way we can use less samples to get tighter confidence intervals. So those are the types of tricks that we're going to learn how to do as we move into the next unit and beyond here. But the point of those tricks is that they give you more power. So the same number of samples gives you tighter confidence intervals if you can get less variance in your system. And so the math that makes all this work is, I know there's so many questions about these outputs here. Is it clear what's being depicted here? This is a little experiment you can do in Excel. It's pretty easy to do. This sort of visually shows you this confidence interval. And so I was saying the confidence interval is just this graphical depiction of a t-test. And so how does that come out? Well, this, if you consider a one sample, two-sided t-test with a significance level alpha, this is your test statistic here. This is your critical t-value you look up in the back of the book. So you could say that, like, if I'm less than that, then I don't reject my hypothesis. I don't reject my hypothesis mu here. If this value here, this statistic that I calculate, is less than this critical value, that's our standard one sample, two-sided t-test. Well, okay, well, let's just unpack that inequality a little bit. So let's imagine that my estimated mean is greater than my hypothetical mean. Well, then I'm in this case where this inequality, when I know that this absolute value basically doesn't do anything, doesn't flip the signs, then I know that this inequality for this case can be written this way, where it just says that the hypothetical mean is in between the estimated mean and this estimated mean minus what will become our half width. Likewise, in the alternate case, where my estimated mean is less than my hypothetical mean, then the absolute value flips the order of these by applying a -1. So I know that in this case, then I'm in this situation where my hypothetical mean is on the right of my estimated mean, and it's bounded above by this half width. So we combine those two together and we get the confidence interval. So that confidence interval there, x minus h, well, there's my h for the minus h, x plus h, well, there's my plus h down here. So to say that something is in the confidence interval is equivalent to saying it's in the range of values that would not be rejected by a t-test. That's all this is. This is saying that, I did not reject mu here, and I did not reject mu here. But this is for the positive case, and this is for the negative case. You combine them together, you get the confidence interval. So that's what the half width, that's what the confidence interval is showing you. It's this geometric interpretation of a t-test. So the probability that your hypothesis is in the confidence interval is equal to, 95%. So if alpha is 0.05, this is 0.95. So it's the probability that you captured the real hypothesis in the confidence interval is 95%. That is what we're modeling here. So the one sample rule is that if you're 95% confidence interval, or if you're whatever, 0.95, so this is 1 minus alpha. So if alpha is 0.05, then this is 0.95. If it's 90%, then alpha is 10%, and so on. If your hypothetical mean is outside the interval, you don't have to do a t-test. You know that p is less than 0.05 or less than 0.1, whatever. So it was 95% and it's outside the confidence interval, p is less than 0.05. It's a 90% confidence interval and it's outside the confidence interval, p is less than 0.1, and so on. If it's 100% confidence interval, and that's a single point, well, then everything is going to be outside of that interval. And in that case, p is equal to 0. It's less than or equal to 0. So that's what it means to be outside the confidence interval, is we reject the hypothesis. So bam, if somebody generates data and summarize and gives you a confidence interval, you immediately can do stats just by looking at the confidence interval. You don't have to do a t-test, because the generation of the confidence interval was like a continuum of t-tests that were done for you immediately. Okay, so questions about this? That's our interpretation of what it means to be a 95% confidence interval. Okay, so there are other rules that are very convenient that just happen to work out in special cases. So if you generate a bunch of data, so this is more getting to relative performance measures, so the next unit, but if you happen to generate a bunch of data and just summarize it with a confidence interval, and you generate another bunch of data and summarize it with a confidence interval, you can compare those two confidence intervals together, and based on how they relate, you effectively do a two-sample t-test without ever actually having to plug in the formulas for a two-sample t-test. So the idea here is that if two of these independent confidence intervals do not overlap, so one confidence interval is completely disjoint from another confidence interval, there's daylight in between them, then the data are significantly different at your level alpha. So if there are two 95% confidence intervals, they don't overlap, then the result of a two-sample t-test, if you were to run one on those same data, would be p less than 0.05. It would reject the null that they come from the same distribution. That is super convenient. And that's, and then if somebody instead plots the standard error of the mean, just because that's their style, but you are pretty confident that the data are normally distributed, then you can just generate confidence intervals by doubling the standard error of the mean, because for enough data, then this critical t value, which scales the standard error of the mean to turn it into the half width, is about 2. So very quickly, if somebody generates two in a bar plot or something like that, or just mean plus or minus error bars, if there's a mean here with standard error and mean, and another mean here with standard error and mean, and you double those, and there's still a lot of daylight in between them, you've done a two-sample t-test just by looking at the graph. You don't actually have to get access to the data to do that test. You know that p is less than 0.05. So that's kind of a fun little shorthand rule. And so I think, example here. So if we had data from a control, here's the mean. And in this case, they've indicated these are standard error bars. Here's a treatment, there's the mean, here are standard error bars. So this could be simulation A, this could be simulation B, for example. Because it's true that the standard error bars do not overlap. But if you double them so that this goes down twice as far and this goes up twice as far, they definitely do overlap. So for this case, I cannot conclude anything without a formal two-sample t-test. But if there was a slightly stronger effect, so the treatment was just a little lower, then if I double these standard error bars so that the resulting estimate of the confidence intervals do not overlap, I don't even have to do formal stats. I know that p is less than 0.05. Now that only works with two groups. Once you go to 3 groups, 4 groups, 5 groups, you can't really do what I just said there. But if you just get 2 groups of data, like control and treatment, then it's a very quick way to evaluate that without having to do any other stats. So questions about that? Is it clear what I mean, or is it clear to you what I'm trying to say here about these confidence intervals being not overlapping and what you can infer from that? Okay. All right. So other cool things that you can do for confidence intervals. So a confidence interval bundled into the half width, there's the number of replications and there's the standard deviation. So if somebody, and the middle of the confidence interval is the estimated mean. So basically you can then back out the, well, the middle of the confidence interval, we could call that an estimate of the mean, X bar. But then if we know the half width, and if we're told the number of replications, and we're told what confidence level the confidence interval is, then we can plug all of that in to sort of an inverse formula for the half width here and solve for the standard deviation. And if the data are normally distributed, which they should be before you even generate a confidence interval, then we now have all of the parameters to generate the CDF of the data, an approximate CDF of the data. So now we not only have the summary statistics, the mean and standard deviation, we now have the whole distribution. So if somebody gives you a confidence interval, they're telling you a lot about the data. It's approximately normally distributed, and here are the mean and standard deviation all bundled up into one little package, which then you can unbundle. And then you can use this to generate new confidence intervals. That's, I think, what you'll do on the homework, where I think there's, or maybe on the lab, where there's one point where we tell you to convert a 95% confidence interval to a 90% confidence interval. Well, if you kind of look at this, you can figure out how to back out the standard deviation and then use a different critical T value to generate the new half width. But more practically, if somebody gives you a summary of their data with a confidence interval, then they've effectively given you an estimate of the whole distribution of the data, which, you just plug into the normal. So that's another cool thing that you can do with confidence intervals. And technically, you could do that with the standard error of the mean as well, if you also knew the data were normally distributed. That's the kind of hidden thing about a confidence interval, is no one should honestly be generating confidence intervals unless they know something about the normality of the data. So all packed in one thing, the confidence interval tells you the data are normal, here's the standard deviation, here's the mean. That's the whole distribution right there in one little interval. Okay, questions? So from here on out, whenever you generate a mean, generate the interval around that mean, because means are meaningless, ironically. But confidence intervals actually have value. Okay. So we also talked about the prediction interval. This is one that is a little less used, a little less important. I need you to know it, and I want you to know it. And once you know the confidence interval, the prediction interval feels kind of a natural extension to that. The formula basically just, instead of doing S divided by square root of R, you do S times square root of 1 plus 1 over R. So it's like if you got rid of this 1, then it would be the confidence interval, right? It would just be S times square root of 1 over R, and then that just becomes the confidence interval. So we're just inserting this 1 plus under the radical, and that gives us the prediction interval. And why do we do that? Well, the confidence interval is giving us a amount of, it tells us about the mean and our estimate of the mean. This is effectively telling us about an estimate of the variance. So we would like to know, given the amount of data we've gathered, not where the mean is in the data, but rather where the next data points we could gather later are. And there are two things that generate variation. There is variation due to the intrinsic variation of the system, the standard deviation, and then there's just variation due to bad luck in sampling, in the sort of drift we get from sampling by too few, having too small of a sample size. And that's what is captured here. The intrinsic variation scaled by the amount of variation added by just the bad luck of sampling too few times. Once you sample enough, then this thing collapses to just the natural variation in the system. And so at that point, you've got a good estimate of the standard deviation. So this interval basically tells you that if you calculate this interval, this prediction interval, a 95% prediction interval, then it sort of means that there is a 95% chance that the next data you generate from the system will land in that interval. Not the mean, the actual data point. All right, so any questions about that difference between the prediction interval and the confidence interval? Very similar quantities. One is estimating the whole spread of the data. One is just trying to get you an estimate of how close you are to the real mean. Okay. And then quantiles, we talked about that last time too, is that you can generate half-widths on quantiles. So we know that the way you generate quantiles is by sorting the data and going to that proportion of the rank order to find that quantile. So the 85th percentile or the 0.85 quantile is just the 85th largest value in the list. Well, every time you generate a new list from a computer simulation, that ranking, that value at that ranking is going to shift around. So there's going to need to be a confidence interval on the quantile. And so basically what we need to know is from what ranking to what other ranking in this data set grabs that confidence interval. So we have this formula for half width, and where P is the quantile you're trying to estimate, R is the number of replications, and this comes from your z-score or your critical z values for a z-test. And instead of just calculating the middle rank, which would be just P times the number of samples, then we say, well, let's subtract from P this half width. And then if we multiply that PL by the number of samples, that tells us the low end of the confidence interval. And if we add that to the P, the quantile we're looking for, that gives us the upper rank. And then if we go from the lower rank to the upper rank, where these are the data at that lower rank, the data at that lower rank, then that ends up becoming a confidence interval on the quantile. So questions about that, about generating confidence intervals on quantiles. Does that make sense? And does the method basically make sense, how half-widths apply? You do this a lot when you have proportionality data, for example, to compare, like, if this in this sim, we have a certain proportionality data, how many people had a wait time longer than a particular amount. There might be some proportion. And then I run the sim again, I get another proportion. I run the sim again, another proportion. And then I want to compare the sims to each other. Well, now I effectively need a confidence interval on the proportions in order to compare to each other. And this is one way to do that. Okay. And then the last thing that we covered last time is when you are running transient simulations of a terminating system. So a representation of a terminating system is a transient simulation. The one question you have is, how many sims do I need to run? You're not allowed to change anything else inside the sim because you care about all of the data in the sim. So the only thing left over is how many replications. So there are two ways to generate that. There's the way that we did on homework H, which is the power analysis. So I won't go over that again, but the basic idea there is I'm going to give you a statistical power. I'm going to tell you what test I'm using, like a t-test, minimum detectable effect size. There are power analyses for chi-square. There are power analyses for any test. And then I run a pilot study to estimate variance, and then I use operating curves to estimate my necessary sample size. That's great because it gives you a nice, strong sample size that you're pretty sure is going to give you exactly the statistical power you need. But a lot of times, statistical power is not the most convenient quantity to communicate to others. So instead, what a lot of people say is like, okay, well, now that we know how to do confidence intervals, then I want you to generate enough replications to make the confidence interval tight within a specification that I give you. So that's what we have now. So that's our new method, where we still have to run a little pilot study to get an idea of how much variability we have in our system, but then we can solve for the number of replications using kind of the inverse of the half-width formula. And that's what we've got here. And so you'll do this, I think you did do this on lab 9. And so the idea here is you just have to make sure that these are independent replications. You have to make sure you've got normality. But if you've got that, then you run your pilot study, say R naught replications, and that generates an S naught estimate of your variance. And then this formula, which is an approximation of the half-width formula, if you look up in the back of the book for a z-test, what the critical z-value is for that confidence level, divide it by that times your estimated standard deviation, divide that by the desired half-width, and this just comes from the half-width formula, then the square of that by the half-width formula ends up giving you a lower bound on the number of replications you need. So you run 10 reps. They say, I want a confidence interval that has a half width less than a minute if I'm estimating some time variable. Then that tells me that that I'm going to need, when I plug it into here, it'll say you need at least 40 replications of your sim to get there. Well, I can use that 10 because it's independent. So I'll just generate 30 more. And then hopefully that 40 has a confidence interval of with a half width less than a minute. If it doesn't, I can generate a few more reps. But this at least puts me in the ballpark. So that is, it's not quite what is rigorous as the power analysis, but is much easier to explain to a stakeholder. Because if they look at these confidence intervals, those are gigantic, then you could say, well, what would be an acceptable confidence interval for you? And they'd say, well, plus or minus a minute. All right, shrink that to a minute, plug that minute into here, and then see how many replications I need to generate those. And then the downside, of course, though, is the more replications you need, the longer it'll take to run your experiment. Because in complex simulations, every replication might itself take a minute. So 40 replications is 40 minutes of computational time. So we'd like to reduce that as much as possible, but sometimes we can't. So questions about that, about choosing replications this way. All right, so that was the sort of the key, that's sort of the key of how we generate these, the key problem with our transient simulations in order to deal with those non-terminating, deal with those terminating sims. So now we have to move on to the non-terminating case. But before we do that, quick eye clicker in the middle here. So I've kind of already given this answer during the lecture, but for the same set of 5 samples of normally distributed data, which of the options below is the largest confidence interval on the mean? So, and this is basically just, if you're clever here, it's probably either A or E, right? So I'm sort of saying that the confidence interval grows or shrinks based on the confidence levels. So what do you think is the largest interval of values? Is it a 1% confidence interval, a 10, an 85, and 95, or a 99% confidence interval? So as you request more confidence in your interval estimate, does the interval get larger or smaller? That's basically what I'm asking here. So what is the largest confidence interval? Basically, is it A or E? So go ahead and put in your answer. And so I guess I can look at the poll here, results so far. So far, some people say A. It's interesting, given that I said it's either A or E, that some people said D. So there's a mix between A and E. There's a lot of people saying E. It'd be funny if I asked you to raise your hands on how many people would say E. So yeah, when I look at this, remember, I'm not grading these based on correctness. It's basically, if you answer this, you're going to get credit for it because I'm looking for just, does your answer make sense for the question? And then these here, wisdom of the crowd, this is what I was looking for. So the idea here is that the more confident you want to be, the only way you can gain confidence is by expanding possibilities. Because as you compress your confidence interval, you're rejecting things. And so as a 0% confidence interval says, I have no confidence the real mean is there. That just basically means I picked a point randomly from the real line. But here at the 99% confidence interval, that's saying that I'm pretty sure that the mean is going to be in this interval. Well, the only way you could be really, really, really sure is if your interval is gigantic. So that's what we're going for there. All right. Any questions about that? Stats look pretty good on it. Okay. So now we do care about number replications for steady state simulations of non-terminating systems, but we have additional things that we can play with now that we only really care about the steady state. So now there's this question of how long do I need to run my sim and how much data do I need to throw out? So that's what we're saying here, is that if you don't throw out enough data here, or if you don't run your sim for a long amount of time, you have a significant risk of initialization bias. So this warm-up period are data that do not relate to the real system. This is just because I had to start my sim somewhere. I took a guess. My guess, because I'm trying to learn about the system, so my guess is going to be off. So I don't want my guess for where to start the system to greatly affect the performance estimate, because then if your neighbor runs their sim, but they initialize it, with this initial point up here, then they're going to get a bias so your two sims are going to converge around a different estimate. If you both run 1,000 replications, you're going to get a really tight confidence interval around a different point because you chose two different initialization schemes. So that's what we mean by initialization bias, and that's what we have to deal with. So so let's see some strategies for that. If I click back. So the typical model of steady state performance measures is that theoretically, this is what a steady state performance measure is in discrete time and in continuous time. It is you basically take the average of these discrete data points. So you're taking an average over an n that goes to infinity, and you sort of look to see, and that effectively gets rid of the impact of any particular small interval and just looks over the entire interval to take that average. So that's theoretically what we're trying to estimate. That's the target in the real world. Likewise, for continuous time data, we're taking an integral from 0 to some length, some duration, where that duration goes to infinity, and we're doing the time average of it. So again, we're trying to estimate this thing right here. But we can't run our sims forever. We have to stop them somewhere. We have to start them somewhere. So our estimate of those two performance metrics are actually going to look more like this. It's going to be an average of a certain length simulation run where we've discarded a certain amount of data. Same thing with a time average. We consider a certain duration that we're taking an integral under, and we take that integral from some point to that point plus that, and then we average over that duration. So we have to choose this T0 or this D, and we have to choose this N or this TE, and we also have to choose initial conditions. So we choose all of those things, and in effect, to eliminate that initialization bias that is just a constant risk when you run these steady state simulations. So we want to not only reduce the bias, but of course we also care about the precision of the estimator, so the replication stuff. We also care about computation time constraints. If we have to run this thing, one simulation replication for 3 days just for one rep, that's probably not good. So we have to balance a lot of things when we're trying to estimate steady state performance measures. Questions about these challenges? Everything makes sense so far? All right, so graphically, we have these early transients we want to get rid of. So common solutions: get rid of this stuff, get rid of this warm-up period, ignore the transient data, and then the other thing is try to make this as close to your estimated steady state as possible. So this warm-up period in Arena, if you go to your replication parameters, I think those who've done Lab 9 have seen that in the replication parameters, there is a warm-up period that you can choose, and it just discards the data from its stats. The other thing is you could go, if you have, say, queuing models from 470, for example, if you look at your system and I can say, well, this system looks kind of like a more simple queuing network that I can kind of do some back of the envelope calculations on, for example, the steady state number of the steady state queue length. So you can, using network theory from 470, you can sort of say with this rough model, on average, the steady state value of people that are in this queue based on my service times and my arrival times is about 6 people. So I can make sure that when I start my system, there are there are ways to do this in Arena. I can start it up so there are 6 people, 6 entities already waiting in that queue. And if I think that's close to my actual steady state, then these transients, this window where it takes the time of this transient to die out, will be a lot shorter. So that's what we mean by intelligent initialization. It's using that background knowledge of how you think the system kind of runs to get much, much closer than just assuming there's nobody in the queue to begin with. But then, of course, that warm-up period, and that will help. This intelligent initialization helps you reduce that warm-up period. So that's kind of what I'm just summarizing here. This is the kind of 470 trick. You look for, these are ways in which you use domain knowledge or modeling knowledge, mathematical modeling, analytical modeling, to guess these initial conditions. The other solution, discard that data in the warm-up period, but then you have to figure out how long this warm-up period is and how long this data collection period is. And so how do we choose, for example, this warm-up period? Well, a lot of this is just going to require pilot studies. So we run a sim like this, and this is the output from, let's say, one replication. And so we can kind of look at this. This is the total WIP history. So these are counts of work in progress. So these are the number of individuals that are in our non-terminating simulations. You can see they start out, they're very low. There are some initial transients. And when you look at this, then you say, well, there's this kind of ramp up period. And then it's like, whoa, there's way too much. And then it backs off. And maybe the steady state's kind of over here. So then you say, well, for this sim, it looks like if I would have truncated whatever this time is, it's like 4 times 10 to the third. So, I take that time and I think, well, I need to probably get rid of all of these data. So, but I mean, that's from a single simulation run. There are, multiple simulation runs, and maybe in another simulation run, the transients died out down here. In another simulation run, they might die down here. So ideally, what we'd like to do is sort of take a little bit of an aggregate. So we might have to run multiple replications. Now, fortunately, we don't have to run them very long because we're just trying to estimate how long it takes for the transients to die out. So we can, so here I can say run so I've got, oh, I'm sorry, I jumped ahead. So this plot, I'm trying to say, if you do only run one replication, I can do a cumulative average from that simulation run. So what that means is I'm saying that there's this, for this, I'm what I'm averaging data in the run to smooth out those variations. So it's hard to see, unfortunately, on this graph here, but these dark line, that's the actual raw cycle times that I'm trying to estimate. And then the gray lines, which are hugging close here, are this averaging process where I'm estimating, like I'm taking an average of this kind of window. So imagine a window of times that I'm averaging and replacing that, and then I'm sweeping this window over, and then that creates a smoother line. And maybe that averaged window helps get rid of some of this junk. So it gets averaged out. So instead of getting this thing that goes up and then comes down, then maybe it smooths out so that it looks more like I've got a transient period and a steady state period. And so maybe you look at this and say, well, there's this, whereas this thing, the black one's got a lot of movement, the gray one kind of ramps up and then seems to settle out. So maybe this time here, that marks my warm-up period. Now, another alternative, which is what I jumped to here, is, well, what if I do multiple replications? I don't have to run them very long, but I have to run them long enough that I think is long enough for me to estimate this transient time. If I plot them all on top of each other, it's a little hard to see the pattern. So every color is a different simulation run. Some of them, it might be hard to see. This purple one, maybe it gets rid of its transients early. Maybe this green one, though, like it looks like it might still be in a transient, by the end of this interval. So what I can do about that is I can actually take an ensemble average. So at every point, I look across all of the replications and generate a confidence interval. So what is being plotted here in this textbook example is the black line is the middle of a confidence interval, and the two gray dotted lines are the upper part of the confidence interval and the lower part of the confidence interval. So for every time point, so if I were to go back here, I could say for point two, well, if I go straight up on point two, let's say, you know, how many colors are in here? Let's say there's 5 different replications here. I get 5 data points at time two. So time two, there's the red data point, the purple data point, the green data point, the blue data point, and the black data point. I take those 5 and I generate a confidence interval just for time two. And then I do that for all times. And then that gives me a plot that looks like this. And that then, by averaging across those, gives me a much more meaningful value. So here it really looks like, okay, so maybe transients appear to die out, like to be safe, maybe around here, around this time right here. Maybe I'll go a little farther to be safe. But this is far less noisy. If it's still a little noisy for you, you can kind of combine the sort of ideas and you can take a moving average as well, a smooth curve. So you can do some data processing on this confidence interval to make it an even smoother estimate of the confidence interval. These are all sort of ad hoc processes. There's no one good way to do it, but you're sort of getting an idea. It's like, I need decision support. I, as the designer here, am trying to make a decision about the sim, and there will not be a perfect answer. But I know that the longer I make my warm-up period, the more wasted time I have throwing away data. So I'm trying to make an intelligent stance as much as possible, because I know that if I don't make my warm-up period long enough, I'm going to get this really bad initialization bias. So that's, again, I'm not saying there's a perfect way, but I'm just trying to give you, there are tools. This I think is pretty good. If it's not that, then smoothing it out, then there are other things. Like if you've done any time series analysis, or if you plan, or if you end up doing any time series analysis, you'll learn additional tools to do that can be applied to smooth this stuff out and estimate where these points are. And as you learn more about regression analysis, there's ways you could regress a point. You could say, what is the best set of 2 lines that I could fit to this, where one line has a horizontal slope and the other one has any slope, and there's a point that breaks those. And so can I actually use other statistical methods to estimate this breakpoint? There are other things you could try. These are just some things I'm kind of using to warm up the idea of where to find the end of the warm-up period. But there's no perfect solution. But hopefully you understand the main gist of it, like what you're shooting for, what the risks are of going too far or too little. So with that, any questions about warm-up period? Okay, so there's one other half of that, which is the idea of how long to run the sim, and also how many replications to run. So we have to deal with that as well. So hopefully we've reduced initialization bias from the warm-up to a negligible level. So which case this basically turns into the same analysis we did with our transient simulations. How many reps to run? And so we can then use that same formula that we did in the transient simulation case for the terminating systems to estimate the number of replications we need. But there may still be other bias left over. We just couldn't get a warm-up period, big enough. So what else can we do? Well, we can if the warm-up period just isn't doing it, then the other half of that is pushing the sim's runtime out farther. So there are general rules that you can use that tend to work okay. So for example, if you have n data points with D discarded in your warm-up period, you generally want to make sure that your n is kind of big enough so that the actual data you keep is at least 10 times the data you discard. Or in other words, the end time of your sim needs to be at least 10 times the length of your warm-up period. Again, that's not a hard and fast rule, but it tends to work. It's hopefully conservative. The longer, as we'll see, the longer you make your sim, that actually has a nice impact on getting rid of a lot of the ugly transients or the effect of those transients. After you do that, then try to increase the number of replications, make them as high as possible. But once you hit 25 or so, there's diminishing marginal returns from adding more replications. There's not a lot of difference between going from 25 reps to 30 reps and so on. Once you've hit 25, generally speaking, there's not a whole lot of value to add more. So you can get actually more bang for your buck in a way we're just about to show by keeping your replications at 25 and use that actual extra computational budget that you were going to put into more replications and instead make each of these replications longer. So let's see how that works. So the idea here is that if I increase, so for a desired precision, I indicate that I need this many additional replications. So if I, instead of running additional replications, I can use my existing number of replications, R naught, and I can extend their run length by that same factor. And I tend to get the same impact on reduced variance. So I get the same, instead of basically, instead of affecting the square root of R in the standard error mean, I affect S in the standard error mean. So instead of making the square root of R bigger, I make the S smaller by doing this, by making this steady state estimate run longer. Now I do it in a very special way. I extend the end time by this factor, R over R naught, but I also make sure I extend the initialization phase. And that's the beautiful thing here, is that not only am I making the runtime longer, but I'm throwing away more data in the beginning. And so I'm making that warm-up period, I'm getting rid of more of the initialization junk that's causing the problem. And I'm also washing it out with more good data. So I'm doing two things at once. And both of those things end up reducing the initialization, but then also reducing the variance in from run to run to run, which allows me to do this instead of adding more replications. So that's why on that previous slide, say once you hit 25 reps, do this, because this not only gives you the effect of adding more reps, but it also reduces your initialization bias. Okay, questions about that? Okay, so the last thing that I want to mention is batching. So if you run lots and lots of reps with warm-up periods, it sort of really hurts to know that so much of your computational time is going to be generating data that's just discarded. So it would really be nice if you could just run a really, really, really long single replication that discards, has a warm-up period that's discarded, but then manages to chop up all of the other data that's generated into batches that act like independent replications, because aggregating over these data will generate a performance metric that's independent of the performance metric generated from aggregating over these, and so on and so forth. And that can happen if this is long enough. So that is one other way to estimate steady state variables and reduce the computational cost of this warm-up period. And Arena will try to do this for you. So if you tell Arena to run a very, 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 very long simulation, then if there is a variable that it thinks you might want to estimate the steady state value of, it will automatically create batches of sufficient length to guarantee independence. And then it will report to you that this is why sometimes Arena in that Excel will give you confidence intervals within a replication, because it'll say like, oh, your weight, and it's like, where does that come from? I thought confidence intervals were generated across replications. Well, that's because Arena found a piece of data that it thought you might want a steady state average of, and you managed to give it long enough period of it that it was able to estimate the length of these things to be long enough that it could create miniature replications inside a single replication. And that's what we refer to as batch means. So you're generating multiple means within one replication, so-called batch means. So one replication does the work of K. Arena automatically does this for you if the replication's long enough. This is also why sometimes when you run short replications in the individual replication data for particular parts, it'll say like insufficient amount of data or something. It'll start just like insufficient when it tries to calculate these half widths. So what that means is it tried to do batch means for you inside a replication, but your replications is too short for it to guarantee independence. And so it threw up its hands and said, I can't do that. But that's okay, because normally you're running multiple replications and you don't actually want batch means, but it generates them. So just in case you're trying to run one long replication so that you can pay the warm-up cost once and get lots of different outputs out of it, then it will automatically do that for you. That's what batch means are. If you have to manually do this, then there are tools like a parallelogram that you can use in the output analyzer. So you can have replicate, like this is replication 1 of the Lab 9 manufacturing system, and you can ask how auto-correlated are the data with each other. And what this is saying, these blue bars saying that up to this number of samples or this number of lags, then these data are significantly positively correlated with each other. These are negatively correlated with each other. So there's a particular point where the correlation, let's say out here, drops to a small amount. Like it doesn't matter if it's positive or negative, both are correlated. But if the magnitude is small, then you could say, after 100 lags, after 100 samples, then I'm pretty sure that these data are independent of these data. So maybe my batch size should be at least as long as 100. This is what Arena is doing behind the scenes when it tries to do this for you. So you can generate these parallelograms in other tools. This is one generated in MATLAB, and it shows you that like once you get under this significance level, that could be the length of your batch. Generally, once you figure out where you sort of lose correlation, you multiply that by 10, and that gives you a safe size for your batching. So that's what's going on behind the scenes. So that's all I've got. So any questions about batch means? These are all methods for generating steady state performance metrics. All right, so let's end with this then. So which of the following is not affected by an increase in replications? The 95% confidence interval, the mean estimator variability, the computational time required, or the estimator bias. And so if you increase your number of replications, my claim, and so again, I'm giving away that E isn't an answer here. My claim is that all but one of these four change when the number of replications is changed. But one of them you can't change by adding more replications. So go ahead and give that a shot, and that's all I've got for you. So we'll see you Thursday.